Welcome back. Time to rationalize the following lattice energy values. I'm gonna actually block this out, and we will predict. We'll hypothesize, and then if these values match our hypothesis, then that will have been the rationalizing. All right. So lattice energy is described by some constant K, Coulomb's constant, times the charges of those ions, Q1 and Q2, over the distance that separates those ions, which is determined by the size of those ions. So what do you think is a greater factor in determining the lattice energy of ionic compounds? Do you think it's the charges of those ions, or do you think it's the radii of those ions? Well, it turns out it's the charge of the ions. So we'll test this out. The numerator is the product of two charges. That's going to have a greater effect than the size of the radii, which oftentimes are very similar. All right, so let's compare in our first test here, the first two compounds. The first two compounds have the same anion, the selenide anion. So when selenium loses 2 electrons, well, all these elements in group 16, they're going to want to gain 2 electrons to achieve the octet rule. So their most stable ion will have a 2 negative charge. Now, the difference is the cations. Calcium, being in group 2, is going to lose 2 electrons and form its most stable ion with a 2 positive charge. And sodium, being a group 1 metal, will lose 1 of its electrons, its only valence electron, to form a 1 positive cation. All right, so what I'm saying here is if we're comparing the first two compounds, the charges are going to look like this. All right, so for calcium selenide, it's going to have, all right, we're going to disregard the K for now. The charge on calcium is a 2 positive, the selenide is 2 negative, and the R is not really going to matter here. Now for sodium selenide, the charge is going to be 1 positive times 2 negative, 2 negative times some R, and that's really not going to matter as much. Right? So we would expect the lattice energy for calcium selenide to be much greater than the lattice energy for sodium selenide. Let's put that down here. Calcium selenide, much greater than sodium selenide. All right, let's compare the other two now. This one, calcium telluride and sodium telluride. So again, we have the same scenario where the anions are the same. By the way, it's also going to be 2 negative because it's in group 16. And the cations are actually the same cations. So again, for the same reason, we can say calcium telluride should have a much greater lattice energy than sodium telluride. All right, now let's consider the size of the. We're going to compare the size of the ions. So when we compare, well, we just did that. How are we going? All right, here we go. Let's compare sodium and here we go, calcium and calcium. So this, if we compare these two, the cations are the same, but the anions are different. But the anions are not different in charge. They both have a 2 negative charge, but they do differ in radii. So the selenide ion is smaller than the telluride ion because it's higher up in the periodic table. So let's do the, all right, so we're going to compare this time the calcium selenide, which is going to have the Q's going to be the same. It's going to be 2 positive times 2 negative, and the radius for this, we'll just put a down arrow, means it's smaller. I don't feel like looking that up. We're just comparing anyway. All right, and then for the calcium telluride, the charges are again going to be the same. By the way, since we're talking about charges, these are not the actual charges. These are just the integer values we're using for comparison purposes. Right? But if you were to get exact calculations and numbers, you would use the actual charge of the electron and proton. All right, and this one here is larger. The radius is larger because telluride has got all those extra electrons. It's got 52, or 54 rather, because it gained 2. All right, because the radius is smaller of the selenide ion, we would expect the lattice energy of calcium selenide to be slightly larger than the lattice energy of calcium telluride, right? Because our hypothesis at the very beginning was saying the radius is a smaller factor than the charges. Okay. All right, so calcium selenide has a greater lattice energy than calcium telluride because of the radius. All right, what did I just say? Calcium selenide greater than. All right, so calcium selenide is greater, but not much greater. Let's compare the other two now, the last two. If we compare the second and fourth compounds, again, the cations are the same, but the anions are different. It's the same anion, so we already know we're going to expect, for the same reason we just talked about, sodium selenide to have greater lattice energy than sodium telluride, because this one here has a smaller radius, ionic radius. All right, so sodium selenide is going to have a greater lattice energy, not by much though. Oh man, I just realized that's not sulfur, that's selenide. All right, then it's two of those guys. Then that. Okay, let's see. How do we rearrange all of these now? So we're going to rearrange everything we have on the screen. This guy's going to have the largest, right? Lattice energy. And then this one is going to be slightly less, right? I'm just copying there. All right, so we've done that part. Now, this is much greater than sodium telluride, so let's do that. Actually, this guy we need to squeeze in there too. So, yeah, let's do that. All right, it's still going to be much greater because the difference here are the charges. The Q's are different. And then this one is going to be only slightly, has a slightly larger lattice energy than sodium telluride because, again, that's based off the radius. So the big jumps here are going to be because of the charges right there. That's why I got the double greater than sign. All right, so let's see how we did. I'm going to go up here. I can unblock that. I'm going to be right back. All right, so I have just copied and pasted that again. So let's see if this works. That guy goes there. That guy goes there. That guy goes right there. And this guy goes here. Whoa. Huh. Get out of here. There we go. All right, so were we correct? This is definitely larger than that. This is definitely much larger than that. And this is definitely larger than that. So there we go. Sum it up. The Q's have a greater effect than the R.